Thanks so much for coming, everyone. I know this is like, it's a busy time, it's midterms, it's everything, but you guys still found the time to come here. One that shows you guys are very dedicated about this, and also I hope that shows that I'm a good lecturer. Yeah, so good news all around. Okay. And your reward for coming here during such a busy time is you get to listen to the most important RL lecture of this series. Because let's be real, like the past 2 weeks, what you've been learning have is important, right? It's the foundation of RL. But those algorithms, you'll rarely get to use them in the real world. Because, well, you'll see why. So today you'll actually learn about the algorithms that you can actually apply to our problems, and this lecture will serve as the springboard for all your future R endeavors, because pretty much all our algorithms are built on the principles of Q learning, which we'll cover today. So yeah, get excited. Let's get started. So normally I start with like an AI thing, like an AI news, but I forgot this week. So I'm gonna replace it with this. Make sure to follow our socials. There will be a tournament happening in reading week. Make sure to not miss that. Okay, it's gonna be great if you want to apply RL. But just because I didn't post any AI stuff doesn't mean there's been no AI stuff. I'm sure there's been like 200,000 papers that's been published between now and last week. So yeah, let's get into it. So I really hope for those of you that weren't here last week, you watched the video of last week's lecture, because if you didn't, you might find this lecture a bit challenging. But yeah, so here's the recap. So last week we talked about the Bellman equations. I hope you guys remember this. Once again, there's a lot of math here, but just I hope you get the intuition, right? Right. The value of, let's say, the current state is equal to the value of the next state plus the reward, and accounting for all the randomness of the policy and the environment. Same with the Q value, except it's about states and actions, right? The states and actions, or the value of the current state and action is equal to the value of the next states and next actions plus the reward, right? Makes sense. It's dynamic programming. What their solution now depends on your solution down the line, right? Plus, once again, the randomness. So these are the regular Bellman equations, but then you have the Bellman optimality equations, which talk about the optimal value function and the optimal Q function, or the best value and Q function you can get in this particular environment. And since we care about the best, this eliminates the randomness in the policy, right? Because we no longer care about the other actions, we care about the best action. So we just take the max of the actions for the value case, the current action in the current state. Or for the Q value case, you take the max over the next actions in the next state. I hope this is a good recap for everyone. If you have no idea what these equations mean, well, today is going to be pretty rough for you, so I recommend you review the recording from last week. So recall, this is just an application. We did this example last week. This is just an application of this Bellman equation, right, for value, right? So the value of the current state is equal to the probability of taking these actions according to the policy, so 0.4 and 0.6, plus the reward you get, right? In this case, so in this branch is +5, plus the randomness of the policy, so 0.25 and 0.75, times the values of the next state, right? Once again, this is all review. And of course, you have the discount factor, and you have the other branch to account for, the 0.6 branch, right? With the -10 reward, but no randomness in the dynamics. Okay, this is once again just review of this Bellman equation. You're just applying this Bellman equation. And this is the application of the Bellman equation for Q, this one, right? You have the reward. Once again, there's no more randomness. No, you don't care about the policy in this state anymore, right? Because we have already predetermined which action we care about, which is the right action. So it doesn't matter if it's only got a 1% chance. We want to work with that action. You get the rewards, right? You account for the randomness of the environment, and you add up the values of the next state action pairs, right? So here you do 2 times 0.8 plus 4 times 0.2, which gets you 2.4. And you do the same elsewhere. And yeah, this is just the Bellman equation for this Q function. Right. And so this is the dynamic programming updates at each time step. You consider all the next states reachable from the current state. So here, right, this is the state. These are actions. These 4 are the next reachable states. You update all of it, right? Or you use all the information here to update your value for this state. And we talk about policy iteration. This is an algorithm that achieves the optimal policy for an environment where you initialize a random policy, you evaluate the policy, right? Find its value function using the Bellman equations we just talked about. Then we improve the policy by acting greedily with respect to the policy, and we repeat until the policy is optimal. And this is how you act greedily with respect to a policy, right? For if you have the value function, you sort of just pick the best action for this value function. And if it's the Q function, right, you just sort of pick, once again, the best action. We'll get into this a bit later. But one question I want to think about is, which one would you prefer, right? I mean, there's two possible value functions you're going to learn here, V and Q. And there's two ways of getting the optimal policy. Which one would you use, right? Keep that in the question, keep that question in the back of your mind. Okay, that's the recap of last week. Once again, it's a very watered down recap. So, and you'll be missing a lot if you don't watch the lecture from last week. So yeah, please go do that. Now, I know we just spent a week or a lecture talking about dynamic programming, but there's a big issue with it. What could that be? So let's consider the following situation, okay? Can someone tell me, I mean, recall, this is like the exact same scenario as the example we just did, right? But, okay, so can someone tell me like what the value of A is? Or how would you find it? Right? It's not possible, right? Because, why? Because you don't know the transition dynamics here, right? Before it was, I think, 25% you go here, 75% you go here or something. That specifies one value function. But what if you had a 1% chance of going here and a 99% chance of going here instead, right? The value would be lower because you'd be more biased towards the state with lower value. On the contrary, if you had a 99% chance of going here and a 1% chance of going here, it'd be reversed. The value would be higher because you'd be biased towards the higher value state, right? And well, if you think about it, like in the real world, right? Do you always know the dynamics, like the probabilities, right? I'd actually say like in no cases would you know that. Let's say you're trying to build a robot to go on the moon, or you want to build a autonomous driving, just on the street, right? Can you model the weather? Can you model all these sort of, peculiarities and randomness in the environment? You have no idea what these probabilities are. So you cannot use dynamic programming, right? Because you don't know the transition dynamics. And same with Q, right? You cannot know the transition dynamics here, so you can't find the value of this state, because once again, you don't know where the dynamics will take you, right, after you execute this action. I hope this is clear to everyone why you need the transition dynamics to find the value in Q using dynamic programming. And if you remember the Bellman equation, the transition dynamics is part of it, right? P of S prime R given S of A, right? That's two summations, right? If you don't have that, you can't use it to calculate. And yeah, so I mean, this is just a summary, right? So imagine you want to develop a robot that goes around Canada or something, but you need to model the weather, right? Because there's wind that can mess up your robot. How can you know, like, the transition probabilities, quote unquote, of the weather? You cannot. You cannot. So therefore, dynamic programming is very, very limited, only to sort of really small state spaces, very well-known, well-defined like problems where you know the dynamics specifically. Can you use dynamic programming? So there's a big issue there. So we need new options. We need, so in model-free situations, right, where we do not have the model of the environment, or it'd be very expensive to learn the model of the environment. Okay, so I mean, you could technically maybe model the weather, right, using advanced simulations and all these resources, but that's really hard to do. It's really hard to do, right? To first of all, get the money required to buy these simulations and the resources, and second of all, to actually accurately model the weather, because if you have an inaccurate model of weather, that actually would hurt your policy and your model, right? So we need a model-free way of doing RL. And these two methods are what I will tell you today. And these two methods are, well, more temporal difference learning, but these two methods are sort of the foundations of all future RL you'll do, right? Model-free RL you'll do, that is. Even in model-based RL, to be honest. Yeah. 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 When I say model, this is not like, I don't mean like a statistical model. It means like the transition probabilities of the environment. It means like a model of the environment, right? That makes sense. It's not like I don't know, like a red black tree or something, like a model like that. I mean like actually a model of the environment. Yeah. Yeah, you don't know the probability distribution of the environment. It's an unknown probability distribution, right? You don't know where the wind will blow you with what chance. So you need a situation where if you don't know anything about the environment, uh, you still want to do RL. Otherwise, it'd be pretty useless. Okay, we'll start with Monte Carlo methods. The name's pretty fancy, but I hope you'll come to appreciate that it's actually a very simple concept. Okay. But yeah, I mean, easy to remember, right? Monte Carlo. Remember this, so this was in the first lecture. I don't know if you remember this, but we talked about multi-armed bandits, where it's like you pull a slot machine, it gives you some reward, and you want to figure out what slot machine, let's say there are three in front of you, which one to pull. And remember, the way we estimated the how good each slot machine was is to take the average of all the rewards that the slot machine has given you so far, right? Because you don't really know the inner mechanisms, the gear systems, whatever, of the slot machines. All you can do is pull it, it will give you a reward, and then you can judge how good that reward is, right? Does that make sense? And one way to do that is to just, pull it many times and average the results, right? If there's a slot machine that gives you a reward of 10 with a 99% chance and a reward of a billion with 100 with a 1% chance, if you pull the lever 100 times, you'll probably have an understanding of that underlying probability distribution, right? Okay, so let's apply that same knowledge to this. But first, let's recall the definition of V, right? It's a numerical quantification of good or bad a state is, but it's actually really just the expected return, right? What is the return? Recall the return is the total reward you get at every time step, starting from the current state and going to a terminal state, right? Does everyone remember what return is? It's the goal of reinforcement learning. I hope you guys remember that. So yeah, recall that the value function really is just the reward you get now plus the reward you get later plus the reward you get later averaged. Okay, that's where the expected value comes in. So what do Monte Carlo methods do? Okay, you basically all you do. I mean, it's sort of it's like a naive way of doing it, but you learn the value function by simply trying out the policy many times and just averaging the total return you get. Right? It's that simple. It's that simple. Okay. It's kind of like the bandit machines, right? You pull the lever many, many times, you average the reward you get, and that is your estimate of how good that machine is. Yeah. No, there's an example. Hopefully that will make things up. But no, you don't consider immediate reward. You consider a total return. So you start from a state, you go to the end, you count the total return, yeah, and then you repeat that many times and you take the average. Okay. Important things about Monte Carlo, you learn from complete episodes, the entire episode. And more importantly, it makes no assumptions about the environment. It's model free. That might not be 100% clear right now, but hopefully this example will help. So let's say you have this situation, okay? You want the value for state S. You assume a deterministic policy per state. So there's just one action per state and you'll definitely take that action. Okay. But there's randomness here in the dynamics, right? You don't know the dynamics here. You don't know the dynamics here. The gray states are terminal. Okay. These are like the end of the environment. And yeah, so black circles are like actions, right? So here you take an action, you get a +5 reward, and you have some chance of going to A, some chance of going to B. In state A, if you take this action, there's some chance of going to C and D. So in these cases, C, D, E, you take the action, you'll definitely go to the terminal state. Okay, so it's deterministic. There's no transition dynamics here. Same with B, if you take this action, you get -2 reward, you'll definitely go to E. Okay, I hope this setup is clear. Note that it's impossible to find the value of S because you don't know the dynamics. Okay, that's clear to everyone. You can't just use dynamic programming now. First of all, though, a quick exercise. Which states do you know the values of? Here. Remember, the value is the total expected return you get from that state. Yeah, go ahead. Yeah. Correct, exactly, right? The values of C is just 1, or the value of C is 1, the value of D is 4, the value of E is 8, because every time you go to C, D, or E, you'll just go to a terminal state and get these rewards. There's another state whose value you know. Which state is that? B. Exactly, right? Because for B, once you get to B, there's a 100% chance you'll follow this path, right? So there's no randomness in the future rewards you'll get. You don't need to do all that expected value stuff, right? You don't need to care about the dynamics. So the value of B is what? -2 plus, so once again, always remember the discount factor. -2 plus 0.9 times 8 is something, right? Okay. BCDA, just once again, checking that you guys remember what a value is. So let's now determine the path from S to the terminal states, right? There's 3 paths here. SAC, which is actually the name of an extremely important reinforcement learning algorithm. SAD, which is what I am a lot of the time. And SBE, which is, something else. So yeah, but you guys see the paths, right? That goes to terminal states. Okay. But what you don't know is the probabilities you'll take each of these paths. So let's calculate the total return G. Assuming we take each of these paths, okay? For SAC, you get 5. You get a return of 5 here. You go to A, right? And we're assuming you go to C now. You get a reward of 7, right? Once you go from A, right? But once again, discount factor, you weight it down by 0.9. And if you go to C, right, you get a reward of 1 for sure. So, but remember, you have to weight it down twice because there's 2 time steps in the future. That's how discounted return is defined. So the total return for SAC is 12.1. The total return for SAD is 14.5 using the same method. And the total return for SBE is 9.7, right? You just sort of, okay, that should be 0.9 times 2, not 0.2 times 2. That's a mistake. But yeah, you guys get how the return is calculated? No questions here? I just add up the rewards, but, with the discount factor. Now let's assume you start in state S and you just let the agent, like you keep restarting in state S every time you reach a terminal state, and you just let the agent run many, many times. And by many here, I mean 5 times. All right, you let the agent run 5 times and you get the following returns, okay? Recall, these are just these numbers, right? 9.7, 9.7, 9.7, 14.5, 12.1. Okay, so now how would you use that to estimate the value of S? Any ideas? Right? You just take the average. Very simple, right? Because even though you don't know the randomness of the environment here, by simply trying it out many times, the returns here will reflect the randomness, right? You can see that if you look at this, you go to this state, E, more times than you go to A, C, and D. That probably means that this path has a higher probability, like the transition dynamics here have a higher probability than this path up here. Does that make sense to everyone? Just simply by trying out stuff in the environment, you can understand the randomness. Not understand it, but you can sort of model it, because the distribution of the returns you'll get will match the distribution of the environment. So yeah, so the value of state S would be 11.4 from 5 estimates, right? 5 times. And once again, these estimates come from starting a state S, running until the end, and then averaging. So how do you improve your estimate, right? I mean, is this the real, like once again, 11.4 is just an estimate, right? Hang on a sec. I'll get you after I finish this. It's just an estimate, but you want to improve the estimate. So how do you do that, right? How do you make the average more accurate? You just take more samples, right? It's a simple idea in statistics. You just keep, trying it out until you get, so let's say, okay, yeah, let me take a question first, actually. Yeah. Yeah, right? Because that's the definition of the total return. Return plus discounted gamma times the next return plus gamma squared times and gamma cubed, gamma to the power 4, etc. until you reach the end. So let's say you run this 10 times, right? You start in state S, you run it until the end, okay, and you reset at state S, you run it again, you run it again, you run it again, you run it again 10 times. Let's say these are the returns you get. Then your more accurate estimate would be 10.7. It's once again, I mean, it's pretty simple, right? You just like a naive way of doing, you just keep trying it out, right? You don't know the dynamics, who cares? You just try it out, try it out, try it out, right? If there's randomness in the policy, right? Let's say, because in this situation, the policy is deterministic. There's always one action per state, and you always take that action. But even if there was randomness in the policy, you can see that you can just also keep trying it out, right? Because you know, the randomness will be summarized, will be captured by the returns you get. So, I mean, just taking a look at this environment, right? You'll notice that this path, SBE, is much more likely than the other two paths. And then in this branch, you can see that D is less likely than C, right? Because you only have one instance of this 14.5 return, but two instances of this 12.1 return. So even from this, you can sort of almost guess what the underlying transition probabilities are. Okay, so I hope that's clear. That's Monte Carlo. That's it, right? It's like I said, it's got a fancy name, but that's all it is. You just average stuff. Yeah.
But then the amount of samples being fixed for all possible trajectories exponential in the number of states.
Precisely. Yeah, exactly. So I mean, I'm not saying this is the best method, but he's right. If there's 100 paths here, and let's say one path, one of those 100 paths is only a 0.001% chance of going there, then what you need to sample so many times in order for the Monte Carlo method to see that path and take that value into account, right? It's, yeah, you need to do, yeah, go ahead. A loop that never goes to a terminal state. That is a good question. Okay, you guys are getting ahead of me here. That's a good question. Exactly. What if there's a loop? So you gotta ask, is Monte Carlo usable in all situations? Okay, we'll get to that. But notice, we found the value of S, right? But you can also just find the value of A as well, right? Once again, you don't know the value of A as well because there's some randomness here. But notice that the trajectories traversed by S also include A, right? Such as SAC and SAD, right? So therefore, not only do you know the total discounted return from S, you also know the total discounted return from A. So let's just calculate that, right? The discounted return from A to C is 7 plus 0.9 times 1 is 7.9, right? And the total discounted return from A to D is 7 plus 0.9 times 4 is 10.6. Makes sense, right? Just the discounted return from A. And then recall this trajectory of experience here, right? 5 trajectories, right? 3 of these trajectories aren't that useful for finding the value of A because they don't pass through A. But for the 2, you sort of, once again, average it. The value of A, your current estimate, is 7.9 plus 10.6 over 2 is 9.3. Right? Very simple, right? You just, anytime you encounter this state, you just sort of find the total return that, you get starting from it and you just average it. Oh, that makes sense, everyone, right? This is just, I mean, if you know nothing about Monte Carlo, just imagine it's just taking the average, trying things out, taking the average. Yeah, so the point is, for Monte Carlo method, you can estimate the value of successor states starting from the starting state as well, since you know their total return, right? So A in this case. Right, so Monte Carlo methods can be used to calculate the value function of a policy for episodic tasks. What is an episodic task? This relates to a question about the loops. What is an episodic task, right? One which has a end, a chess game, for example. The example I gave last week was, what if there's a loop, right? What if there's it's a what's it called again? Continuing task? Yeah, that's what it's called. What if there's a continuing task? What if the task never ends, right? Let's say you're controlling a nuclear power plant to supply a whole country. You never shut off the power plant because the country needs battery or electricity, right? So therefore, that task never ends, and therefore you cannot use Monte Carlo method for that because there's never a terminal state you can use to calculate the total discounted return from. Does that make sense? So if there's a loop, I don't think, I mean, I guess that could happen, yeah. So if there's a loop, you wouldn't be able to use this method because it will never terminate the episode. You can only use Monte Carlo episodes or methods when the episode terminates, when there's an end to the task. Right, yeah.
All possible outcomes. That's actually supposed to be having something going over.
Yeah, I don't think so, but let me are there any environments where like sometimes it just doesn't end? Maybe, yeah. You can't. I guess, yeah, you can't do that. Yeah. So yeah, so for environments such as like chess games, maybe an Atari game, like I don't know, Pong or something, where there's an end, what like a winner or loser, you can use Monte Carlo methods to just simply sample trajectories and take the average. Okay, so this is sort of a concrete Monte Carlo algorithm, right? Let's say you have a particular state Sn in some environment, and you keep running Monte Carlo, right? The first time Sn is visited in an episode, you increment a counter for that. So you just add like, the visitation frequency, right? +1. After the episode terminates, you calculate the return G and you add it to the current running estimate of that, the value for that state, right? And as you take more samples, the estimate V converges to the actual value function. This is called first visit because you only count when Sn, this state, is visited for the first time in an episode. There's also every visit, meaning that every time Sn is visited in an episode, you increment a counter, right? So if for this particular episode, maybe it loops back to Sn twice, then C, you'd add 2 to that, right? But for first visit, will always add 1. You don't care about the second visit for some reason. And it's the same process, right? You take the total return you get and you sort of just average it. Okay, does everyone understand just Monte Carlo, right? It sounds fancy, but it's just averaging at the end of the day. Now, here's something, just a sort of mathematical thing, which will become important. This is how you take the average, right? Like this expression here, R1 plus Rn, etc., divided by n, right? Makes sense. But notice you'd have to store all the past rewards, right, for 1 to n. Now that's a lot of computation. That's a lot of memory. Is there a way to optimize that? Is there a way to not store all that memory? And actually, yes, you can. So what you will notice here is I'll skip the derivation, but actually the estimate at the next step, right, n+1, is equal to the estimate of at the current step, Qn, plus 1 over n, so the total amount of visits, Rn minus Qn, right? So Qn is sort of the average, the current estimate of the average. Rn is the reward you got just now at this time step. You just sort of subtracted it. You can think of this term as sort of an error term, right? Because Rn will make your estimate more accurate since it's coming from the real environment. This is almost an error term. You want Qn to be close to Rn, right? Right? Or not close to Rn, but like Rn informs Qn. Does everyone get that? Like since it comes from the real environment. So this is almost an error term. And you do Qn plus some step size plus some step size times the sort of direction of the new estimate, Rn, right? Because this will pull Qn in the direction of Rn. Does everyone get that? Okay. But the point is, you don't need to store all the past rewards. You can sort of recursively express Qn+1 in terms of just Qn and your current estimate. Yeah.
So are those two?
Yeah, they are. So this is a very important form of equation you'll see in reinforcement learning. And by very important, I mean it's literally everywhere. The new estimate is equal to the old estimate plus some step size times the target minus the old estimate. The target here is like the thing you're regressing to, or the actual signal, like the ground truth sort of true thing you want to be estimating, right? In here, it's the reward, right? Because you actually want the average reward for this particular environment. So that's the target. For Monte Carlo, though, it's the return. Notice the value of Sn, right, for a particular state is equal to, so this is updating the value. There should be an arrow here. This is not, so Vsn plus the count, right, the step size. Recall, this is just the count. G of n minus Vsn. It's literally the same thing here. 1 over n, 1 over Cs, and R minus Qn, G minus V. right? Where G here is the target, it's the total return. Okay. And so this is the Monte Carlo expression, right? No one actually sort of remembers all the returns you get from like 10,000 times of trying. You incrementally update. You only keep the current estimate. Every time you get a one new trajectory, you apply this equation and you get the new value estimate. And so so instead of 1 over CS here, you just sort of replace it with an alpha, some step size. It's a hyperparameter. You can choose whatever it is. Okay. If you want the changes to be more drastic, you set alpha to a bigger number. If you want no change, for some reason, you set to 0, right? In that case, VS will just never change. Everyone understand that? And it's very important. Almost all the algorithms we'll investigate later on will have an equation of this form. All right, once again, remember this. New estimate is old estimate plus some step size times the target minus the old estimate. Okay, and this seems fancy, but all it's really doing is taking the average. All right, just another way of saying take the average, but in a more efficient manner. Okay, very important. I hope you guys remember this. This is still Monte Carlo, still taking the average, even though it doesn't look like it. Let's just do a quick example, right? Let's say the current estimate of your value is 50. Okay, V of S equals 50. Let's say the step size is 1, and let's say you start from this state, you run it towards the end, and for this particular episode, you get 20 return. What do you do here? You do 50 plus 1 times 20 minus 50 is 20. So this is your new estimate. Notice that it sort of dragged your old estimate closer to 20, right? Because 20 is the truth, is the ground truth thing you got. It's the accurate estimate, right? It's like the actual return. You want your estimate to match that. And by doing this, you drag your estimate to be more accurate. Does everyone see that? So notice here, you don't need to keep all your past returns. As long as you have the old estimate and the most recent return, you just care about that. How easy and quick this is, right? How efficient this is. So if you remember a dynamic programming update with the little triangle that considers all next states, at each time step, you start at a state, you run it towards the end, and you use these states as the update. Notice the difference between dynamic programming, right? You no longer consider all the next states, you run to the end and use the return here. Okay, I hope this makes sense to everyone. Any questions before I move on to temporal difference learning? Okay, great, right? Simple, right? Just take the average. Okay, temporal difference learning. Let's just jump right into it then. Okay, recall, like this is the expression for the return, right? If you guys remember, RT plus 1 plus RT plus 2 plus excuse me, yeah. Gamma times RT plus 2 plus gamma squared RT plus 3. I just realized something. I forgot to record this. That's crazy. What is okay? Um, okay, wait. Sorry, guys. Sorry. Give me a sec. Give me a sec. Think about temporal difference for now. I mean, Monte Carlo for now. Oh no, I was recording. I'm stupid. Okay. Oh, I just wasted a bunch of time for no reason. Okay. Sorry, guys. It's been a long day. Jessica must have started. Oh no, please. No. Okay. We're back. Okay. Sorry about that. For the return, right? Notice that you can express the current return as the return at the next time step. Does everyone see this? Right? RT plus 1 plus gamma times the rest of the return, right? Does everyone see this? All right. And notice how similar this is to this, right? Like it's the current estimate plus something else, right? So the return is R plus T plus 1 plus G of T plus 1, time obviously discounted. Now, same with the value, right? You take this expression, you put it in the value. Recall, this is the definition of the value, right? And what you can do here is you express the current value as RT plus 1 plus gamma times the value at the next state. All right, once again, this is just dynamic programming kind of, but this is a sample based, right? Because it's not the expectation. But everyone see this, like it's just the value of the current state is the return you get or the reward you get plus the value of the next state you go to. Very simple, right? This is called bootstrapping. Recall the expression for the Monte Carlo update, right? This is the Monte Carlo update, right? So what if we just replace G, right? Because recall G is this thing, right? You replace it with this, okay? You replace it with, instead of having G here, you do RT plus 1 plus gamma of V of ST plus 1. Does anyone see this? Once again, it's the same form, right? It's the current estimate plus a step size times a target minus V of ST. Any questions about this? I mean, okay, no, you definitely have questions about this. Let me go through the example, and maybe this will become more clear. You might think, okay, this is kind of weird, right? Like, it's sort of, there's two V's here, right? The return is something you can actually get from the environment. You roll it out, it'll give you a return. But here it's like, it's not the return anymore. It's just the next state value. How does that help, right? Let's consider this scenario again. Once again, it's the same deterministic actions. You don't know like these transitions, right? These states are terminal. Let's assume you want the value of S again, okay? And you initialize all the initial state values to be 0. This is your estimate, your initial guess, right? It's definitely wrong, but you just guess. Let's apply this TD expression, okay? Let's assume alpha is 0.5, right? This step size. Let's assume an agent starts as S. All right, this once again is just a random, trajectory. It goes to B and goes to E. What happens? Let's apply it. The value of S is 0 plus 0.5, right? The step size, plus the reward, which is 5, plus 0.9 times the value of B minus 0, right? Because V of ST right now is 0. And V of B is also 0. So this whole thing just cancels out. So this is just 0.5 times 5 is 2.5. You do the same at B. 0 plus 0.5 times negative 2 plus 0.9 times V of E minus 0 equals negative 1, right? And V of E is 4. Once again, it's just the same expression, but it's just half of 8, half of the reward. Okay, just one, does everyone see what I just did here? I just applied the temporal difference equation to this trajectory. Let's assume, okay, so now we have these, updated values. They're still like pretty bad, right? But let's try it again. Let's go through SBE again. One more time. This time it's 2.5 plus 0.5 times 5, right? This is the reward, and this is the step size, 0.5, plus 0.9, which is discount factor, times the value of B. This time it's no longer 0, it's negative 1, minus 2.5, where 2.5 is the value of S. Once again, it's just applying this expression. And now it's 3.3. You do the same at B, and it's 0.3, right? You do this exact same thing, is 0.3. At V of E, right, you do the exact same thing again, 4 plus 0.5 times 8 minus 4, right? Because the value of this state, the terminal state, is 0. Okay, I forgot to mention that. It's always 0. So 0.9 times the value of the terminal state is just 0, right? So now you have another estimate, 3.3, 0.3, and 6. I want to see what's happening here. We're applying the temporal difference update. Let's do that again, okay? I'm going to go through it faster now, okay? You go through SBE again. You do the same 3.3 plus the step size times the reward plus the discount factor times V of B, which is 0.3, minus 3.3. You get 4.3. You do the same at B. You do the same at E. You get these two numbers. So trust me, you just get these numbers. Let's do it one more time. You do it again, 4.3, blah, 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 okay? Everyone, I'm not going to go through this. You apply the temporal difference update. You get these numbers again. Let's do one more time. Okay, I know this is getting old, but I think this is the last one. You do it again. Okay, 5.5, okay, whatever, right? You get these numbers. Now, remember that we said we know the values of E, right? E and B, right? Because there's no randomness here. What are they? Well, The value of B is -2 plus 0.9 times 8 equals 5.2. And the value of E is 8, right? Because this is the reward you get. Does everyone see why these are the values of B and E? Now, what do you notice about the estimates that we've been doing so far, right? Recall, just look at these numbers, right? It goes from, 1.9 to 3.1 to, it goes from 7 to 7.5 to 7.8. Notice that the values for B and E are getting closer to their actual values the more you try it out, right? Look at E, right? If you recall, initially the increase was very fast, right? It went from 4 to 6, but now it's like slowing down, right? It goes to 7 to 7.5 to 7.8. Okay, now let's go through the other path, right? Let's go through SAC, right? Let's apply the expression. Okay, so V of S is 5.5 plus blah, 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 V of A this time, right? Because you're going to A, and V of A is 0, right? So it'd just be 5.5 plus 0.5 times 5 plus 0 minus 5.5 equals 5.3. Okay, so the V of S went down a little bit. V of A, you do the same, all right? You'd use the value of C for the value of A as the next state. You get 3.5, and the value of C is 0.5. Let's go through SAD this time, right? SAD. You apply it again, and it's just the same expression. I won't go over it again. You get 6.7. Oh, you see the value of S went up. Remember, what was the value of S we estimated with Monte Carlo? It was like 10 or something, 11, right? Okay, so it went back up. Value of A is like 5.25. Remember, what was the value of A we did? Like 9 point something, right? And the value of D is 2, right? Applying the same expression. Let's go through SAC one more time. Once again, okay, so you do this, you get 8.2, value of A is going up, value of C is going up. What number is the value of C approaching? What should it approach? What's the value of C? Exactly, it's 1. But notice it's going from 0.5 to 0.8, okay? Let's go through SAD. What value should D approach? The value of D approach? 4, right? Because the value of D is 4. Okay, let's see if it does do that. Okay, so value of S is going up again. Remember, from Monte Carlo, the value of S was around like what, 10, right? The value of A was around like 9, right? Okay, and then the value of D is 3 now. Okay, so this is what I was saying, right? I forgot to update the values, I think. Yes, my bad. But recall that the values of C and D are 0.8 and 2 respectively. Or no, are 1 and 4 respectively. Notice that as we continually apply the temporal difference update, the values of C and D are approaching these values, right? Now the value of C is like 0.8, which is pretty close to 1, and 3, which is pretty close to 4. You can probably guess that as we do more of this, the value of D will eventually get closer and closer to 4. The value of C will get closer and closer to 1. We only showed that the value of E is very close to 8. The value of B is kind of close to 5.2, which is its real value. So notice that as we apply the temporal difference update, right, the values are getting closer and closer to what they should be. So it's reasonable to assume that the values of S and A, even though we don't know their true values, are getting closer and closer to what they should be as well. And I mean, notice that if you recall, the value of S and A after averaging 5 trajectory samples were 11.1 and 9.3, right? And notice that S and A, they're still a bit off, but they're getting closer, right? Remember, we started from 0. We started from 0. And if you remember, actually, for one of these iterations, the value of S went from 5.5 to 5.3. It went down a little bit, but immediately kind of got corrected as you tried out more experience. This is temporal difference learning. All right. You, instead of going to the end and using that as your estimate, you just sort of take one step and use that as the estimate. It might, like when I first learned about this, it would seem like this wouldn't work, right? Because the next state value is also itself an inaccurate estimate. Do you get that? So why would it work, right? Like, why does this work? If you recall, we all started from zeros for these states, and these values were way off. But why does it work? Well, first of all, there's certain terminal states that have, like sort of the ground truth, right? These rewards, right? So you sort of get a lot of signal about them right away. But also, as you're interacting with the environment, the rewards you get sort of act as the target, if you recall what the target was. These rewards inform your updates. So even though you originally start with wildly off values, as you keep doing these one-step updates, you'll get closer and closer and closer to true value. Does everyone understand that? Someone tell me the difference between Monte Carlo and TD. Someone tell me. Right. Right. Yeah. Yeah. No, no, that's good. That's good. For Monte Carlo, one time step, you go all the way to the terminal state, the gray state, the terminal state. But for temporal difference, you just take one step and then you update already. Does anyone see that? Right? Does everyone see this? Here for V of S, we took one step toward A and we can already update the value. We don't need to wait until here to update. Whereas for Monte Carlo, we have to wait until we got to the terminal state, calculate the total return, and then update. Does everyone see that? Okay. One step temporal difference learning. You start in a state zero, right? You take an action A, receive the reward, and land in some next state S1. When like as soon as you get these information, S0, A0, R1, S1, you can immediately do this update. Okay. And you keep going throughout the trajectory until the episode ends. Or it doesn't end at all. I mean, this is your question earlier. What do you do in continuing environments where the episode doesn't end? Not Monte Carlo, you do this, you do temporal difference. Why? Because every time you take a step, you can update. There's no requirement for it to end. Does everyone see that? Yeah. So what do you mean by like keep the value of A? No, no, you don't go back to zero. That's your initial estimate. That's just so yeah, you start at zero for A. You go through SA you go through SAC, right? This path, SAC. You can up notice the value of S is from going through SBE all those times, right? It's 5. It doesn't reset to zero, right? But after you reach the terminal state, you reset back to S, and this time you're going to SAC, right? And you update the value of A, and then now you're going to SAD. You don't reset A back to zero. Yeah, go ahead. Yeah, sure. I think so. For discrete tabular environments, yes. Yeah. In discrete tabular environments, yes. Yeah. So in grid worlds and like where the state space is finite and the actions are finite. There are infinite dimensional state spaces, right? Like if you have you're controlling the motor of a car or whatever, a robot, the torques are not discrete. The torques are like 0 0.1, 0 0.2, 0 0.15. That's an infinite dimensional state space. No, yeah, you can. But you can use both Monte Carlo and TD for infinite dimensional state space. Um, yeah, if you use I think it might converge if, okay, so this is getting above the scope of this course, but if you use a linear function approximator to estimate the value, I think it might converge, maybe. So for those states, for infinite dimensional state spaces and action spaces, you'd use gradients, gradient descent or stuff to do that. If you do that, I think there's a theorem that if you do a linear function approximator for that, it might converge to something close to the true value. But for general, if you use a neural network, some nonlinear function approximator, there's no guarantee it will converge. None. Yeah. But for our case, so we're not, so if you guys didn't understand that, you don't worry about that. But for our cases, in discrete state action spaces, this will converge. So will Monte Carlo, I think. Yeah, Monte Carlo. In fact, like Monte Carlo might even converge to in like for infinite as well, because if you think about it, you just take the average many times, right? So you'll actually eventually, if you take the average and if you sample an environment infinite amount of times, you'll get the true value. But for TD, I don't think there's a guarantee like that. So does everyone understand TD? What's happening? You take a step, update, take a step, update, take a step, update. It might end, it might not end, whatever. Any more question about TD? It's critically important that you understand what TD is. Because this like sort of paradigm, temporal difference paradigm, is the foundation of like, yeah, most R algorithms. Advanced ones we won't talk about, but you'll experience. Okay. And just to contrast with dynamic programming, because I feel like the two equations look kind of the same, right? Um, in DP, we looked at all possible next states, right? But now we only look at the one possible next state. And this is why it's model free. Because imagine like here, right? This randomness. In dynamic programming, you'd have to consider both of these states when making the update. And so you need to know these probabilities. But for TD, you don't care where you end up because kind of like in Monte Carlo, if you just try it many times, you'll eventually get a good result, right? That's the idea behind dealing with randomness. You just have to try it a bunch of times, okay? So TD, you just try it once, okay? You maybe one time you go to SBE, one time you go to SBE, another time you go to SAC, SAD. It doesn't matter. You just keep trying it. You'll get a good value for S. And so relationship to the Bellman equation. So this is what I've been talking about, sampling. How you deal with randomness, the reason these methods are model-free instead of model-based, right? That they can work without knowing the model is because they sample stuff, right? This is the Bellman equation for V, right? You get all this randomness you have to take into account, the policy, the value, the policy, the dynamics. For the temporal difference expression, it looks very similar, but this is just for one particular state value, right? You don't care about all the next state values. That's why there's a summation here and there isn't one here. You don't care about all the next states. You only care about one of them for this particular update. You assume that as you try this more and more, the other next stage will eventually be reached. You'll eventually see them at least once, and then you can do the update. Does everyone understand why TD and Monte Carlo are sample-based approximations of the Bellman equations, and hence why they do not need a model? Okay, I hope that's clear, right? Because you just deal with randomness, you just sample a bunch. And yeah, this is what is to remember. When there's randomness, when there's an infinite amount of something, when there's so much stuff can't take care of, the machine learning sort of approach is to just try it a bunch. You try it a bunch, and as the number of samples you try approaches infinity, the results will mirror the underlying distribution. That's just the law of large numbers. Like, yeah, I'm gonna understand this. Okay. Now, this is the temporal difference update, right? Unlike dynamic programming, where you consider the whole triangle, unlike Monte Carlo, where you go to the end, you update as soon as you go to the next state. And yeah, so what was different from Monte Carlo? For Monte Carlo, we waited until we got all the experience, right? Right, we took a trajectory, got the total return, right? But for TD learning, every time we took a step, we updated. So which approach should be preferred, right? Here's some questions for you. Recall, this is what is used in Monte Carlo, the return, and this is what is used in the temporal difference target, this. Which one is a better estimate of the value? Like the ground truth value, which is more accurate? Which of these two quantities is a more accurate estimate of value? What'd you say? Exactly. Why? Because recall, value is literally defined as the return, right? So by finding the total return, it's like actually the value. Does everyone understand that? Whereas for TD, your current estimate depends on another estimate, right? V of ST plus 1 is another estimate. Recall our example, right? The value of S depends on the value of A and B, but these are still estimates in of themselves. So they're not as accurate as if you had went all the way to the end and gotten the real actual return. Does everyone get that? Why one's more accurate than the other? Okay, now which takes longer to compute? Exactly, right? Because you have to go to the end of the episode. Now, which one has lower randomness? Or I say randomness here, what I mean is which one has lower variance? Meaning that when you draw a value from, let's say you have like, okay, no, I'll just explain it. I think it'll be more clear if I just explain it. Okay. And think about this for now. Which one do you guys prefer? And I can tell you the answer of which one the industry prefers. Okay. Temporal difference versus Monte Carlo, right? Temporal difference works for both episodic and continuing tasks because it relies on a one-step update, not the total return. It updates immediately. It does not need to wait till the end of the episode. It has higher bias and lower variance. We'll talk about that in just a sec. Monte Carlo only works for episodic tasks. It waits until the end of each episode to update, but it has lower bias and higher variance. So the answer to which one has lower randomness is TD. Okay. Variance is randomness. What is bias? Okay. Bias can be thought about how accurate an estimate is to the true value. This is not the like the technical definition, but this is like the intuitive definition, right? Since Monte Carlo methods use the actual total return to estimate the value, is more accurate than TD because TD is relying on another estimate, right? V of ST plus one. That will understand why Monte Carlo's a lower biased estimator, lower bias, more, it's like a more accurate estimator in a sense. Yeah.
Like, that big one, small step, looks like, well, they can jump on.
Exactly. No, that's perfect. Oh my God. Yeah, that's literally what variance is, right? Variance is thought of how much randomness in an estimate, right? Because Monte Carlo methods use the total return at the end, it means it has to like go through more steps of the environment, and the environment is random. So the value you get at the end is like more random. Whereas for TD, you only take one step, which is less random. I'll show what this means, right? Okay, sorry, I skipped. For bias in our example, right? Recall that the value of S, right, is around 10 or 11, right? That's the real value. We don't know what it is, right? Because we don't know. Um, Monte Carlo was able to get kind of close to that after 10 trajectories. However, for TD, although it was getting there, right, it was still at around 8, right? So Monte Carlo is less biased, right? It's more accurate. Yeah. Yes, it was. So both converge, but one's more accurate. That's kind of weird to think about. But yeah, in this situation, yeah. But for variance, right? Okay. Notice there's two sources of randomness in our environment. Randomness here and randomness here. When it came to Monte Carlo, to reach, let's say you go to SAC or SAD, right? To reach a terminal state, Monte Carlo had to go through two instances of randomness. I don't see that. But for TD, when it goes to SAC or SAD, it only goes through one because it only depends on A. Whereas for Monte Carlo, you have to go to the end. That's less variance, meaning temporal difference has less variance, right? The value estimates are less random. Because let's say you imagine, right, you have a very complex environment with like 100 different branches, which branch into like 10,000 different branches, all of them random, right? For Monte Carlo, if you want to go from the start to end, you have to traverse all those branches, right? How random is that, right? Let's say you get a value of 10, or you get a return of 10 from Monte Carlo. Is that reflective of the underlying value? You don't know because that value has such high variance. There could be another path. Let's say 10 could be an outlier. Let's say most of the sort of returns you get from all the other paths are around 1, but it just so happened that you accidentally went down this path that gave you a return of 10, and you use that to update your estimate. That's high variance. That's randomness. 10 is not representative of the underlying distribution, right? Right? Does everyone see that? But for TD learning, you mitigate that because all that randomness in the future you don't care about. You only care about the one step, right? So there's only one step of randomness. Whereas for Monte Carlo, there could be 10,000 steps of randomness in the future for an episode that is 10,000 steps long. Cool with variance. I mean, I talk to you about this because it's important for RL, but for machine learning, the bias variance trade-off is a very critical sort of idea. So just to introduce it to you now, and hopefully you guys can internalize this a bit later. Like, I hope bias and variance are clear. So I hope you guys answered which one you would prefer in practice. But in research, temporal difference is almost, I mean, I don't really know any like Monte Carlo algorithms. I do know that you guys know AlphaGo, like AlphaZero. That one they use Monte Carlo tree search for that. But oh, and another one. But yeah, most algorithms is temporal difference learning. Why? Yes, temporal difference is higher bias, but less variance means more stable training, right? Because imagine you're trying to train a agent. One moment you get a return of like 0, right? But the next moment you get a return of 10,000. And the next moment you get a return of negative 500. That would be what would happen potentially if you use Monte Carlo, because there's so much variance in the returns you get the agent will like jump here and there and here and there, and the optimizer will just diverge. You will not converge to the real environment, right? For most RL tasks, which are high dimensional, very complex, and infinite state action spaces, convergence is not nowhere near guaranteed. It's a very hard thing to converge. Very hard to train an RL agent for those tasks. So you want the training to be as stable as possible. And the way to do that is to use temporal differential learning because there's less variance. Also, TD is faster than Monte Carlo, right? Consider a task where episodes are 100,000 time steps, right? This is, I mean, very normal, right? Sometimes you have like cars or something like a robot that needs to traverse around a large, field or something. Episodes could be 100,000 time steps. To do one Monte Carlo update, one, right? One, like think about how little information that is, just one number to update, right? You need to run 10,000 time steps. But TD, you would have already done 100,000 updates if you had an episode length of 100,000. So temporal difference is like the thing, right? Yeah, it's what's used. Okay. I hope you guys understand the reasons for that. Lower variance and faster. Any questions before I move on? Yeah. Yeah. Yeah, it's a less accurate value. Yeah. Yeah, but it's got less variance. You care more about because if you recall for our situation, right? Monte Carlo and TD both work, right? Remember our situation. TD was getting there, right? Was getting there, right? The values were converging, right? But it was just less accurate than Monte Carlo, less accurate, right? So TD will work, like it works in practice and everything, but the less variance is much more important in my opinion, because when you're training RL for these really hard tasks, right? This every example we do in this course is like it's like a toy example. It doesn't really matter, right? No one cares about little like 4x4 grid worlds. When you're training a car to like drive along a road, the state space is infinite dimensional. It's probably like 100 element vector. That's a state space with the position of tires, position of pedestrians, all of that. It's so hard, and the actions are probably also like 100 dimensional infinite like vector. In a situation like that, you make like one like RL is known for being very brittle, very hard to converge. If you like do one little update in the wrong direction, boom, it just everything blows up, everything breaks. So you want training to be as stable as possible. That's why TD is preferred over Monte Carlo. And it's faster, right? Like I said. Okay, first of all, if there's a continuing task, you can't even use Monte Carlo. Second of all, if episodes are really long and expensive to compute, then you want to use TD because you want to do those updates, right? Some other questions? Yeah.
Um, Kind of seems like if you want to be accurate, it seems like you still have to go for higher that's still on that path. Um, so,
Yeah, but it's yeah. Yeah, but it's still but it's wait, so what's your point like?
so wait, like, only to faster, like that's the long run.
Because like I mean it's I think first of all empirically, like experimentally, it's been seen that TD and Monte Carlo, they're basically they can do pretty well. TD does pretty well. And yeah, like I mean my example is pretty engineered, right? It's just I put random numbers in there and stuff. But I think in general, TD will do just as well as Monte Carlo. While like, because imagine you've got 100,000 updates versus one update, right? Okay, this was like 3 updates versus one update, right? It's a lot better. Yeah, question. Oh, no, no, okay, sorry. Okay. Okay, moving on. From state value to state action value. Let's consider this. Like, let's assume this is a completely new environment and you're given this optimal value function. Okay, this is not the optimal value function for this grid roll, if you recall, but let's just assume it is. Okay. Rewards are -1 per time step. You're not giving anything else about the environment, and you want to find an optimal policy for this value function. What is the best action in this highlighted state? Okay, I don't know. The arrow shouldn't be there. But what is the best action? The arrow? You guys think it's the arrow? Before I answer that, recall this, right? I mean, if you recall last week, every time I specified an environment, I always said that the environment was deterministic, right? In this grid world, it's implied that the agent moves to the adjacent square after you, like, let's say you go left, right? It will go from 2 to 1, right? For this maze as well, if you go up, it's assumed that you'll end up in this square, right? It's always implied that you'll like just go to the next square. So okay, so now you might be getting, do you guys see what I'm getting at? So what is the best action here? You don't know, right? Because you don't know the quantities, right? What if going left, how do you know going left actually takes you to this square? You don't know the environment. I didn't tell you that it does that, right? Recall the transition dynamics are very random, okay? And recall this is how you get the optimal policy, right? You don't know P of S prime R. Like what if like going left takes you to this state instead, or going left takes you off the screen or anywhere, right? You don't know the number. You don't know the dynamics, right? So without the transition dynamics, we cannot use V of S to get an optimal policy or even improve a policy because we don't know, like in this equation, we don't know where taking action will lead us. So throughout the whole course, we've been talking about state values, V. But in practice, like it's not, no one uses state values to get an optimal policy because it's impossible. You cannot do it without the model. Does understand that, right? Here, going down could lead you to this state instead. Going down could lead you to, so you don't know. So how do you resolve this, right? What can you use instead? I mean, if you take a look at this equation for getting the optimal policy from the value, right? Recall that last week we said the Q is equal to this, right? I hope you guys remember this equation. If you don't understand it, it's very intuitive once again, right? The value of the current state in action is equal to the reward plus the value of the next state you get to, right? Plus the value of the next state you get to plus the reward, right? Accounting for the randomness of the transition. So if you just substitute this into here, you get this expression. So this is why the Q value, the Q function, is so important. It's critically important. It's much more widely used than the value function. Okay. In practice, RL algorithms want to learn the Q function. If you look at all the RL algorithms, you'll always notice there's some like probably some Q in there, right? Like CQL, like SAC, all these algorithms learn a Q function. Why don't they learn a value function? It's precisely because of this. You cannot do control or you cannot find an optimal policy using the value function if you don't have the dynamics. But notice this expression, right? If you have the optimal Q function, you don't care about the dynamics. You just look at which action has the highest state value, and that action is automatically the best action, right? Let's see why. Okay, just to motivate this even more. Last week, remember this, right? It was policy iteration. You first find the value of policy, you gridify the policy, you repeat, you repeat, you repeat, repeat. But last week we assumed we did it with dynamic programming. We assumed we knew the model, right? But let's say we don't have the model now. Does this work without the model? Like which step breaks without the model? Policy evaluation or improvement? Policy improvement, right? Because as we said, for V, you need the model to get the best action to improve the policy. But here you cannot, right? You cannot improve the policy after you found its value function because you don't know the model. But on the other hand, this is possible with Q, right? Because you evaluate the policy to get the Q function, and you just apply this equation. You just pick the best state action value without the model, and you can improve the policy. And so you can do model-free policy iteration with only the Q function. All right, this is it. Okay, let's say you have this environment now. You're given the Q function, right? So, okay, once again, how many actions are, I guess it says here. So there are 4 actions, right? So there's 4 Q values per state, right? Makes sense. I hope you guys know why. You're not given anything about the environment. What is the best action in this state? Up, down, left, or right? Can someone tell me? Right? Okay. What about this one? Up, down, left, or right? Up. Precisely. Notice how easy it is to do policy improvement with the Q value. You know nothing about the environment. You just look at the Q value. You just pick the biggest one. It's model free. They don't understand why the Q value is so much more valuable than the V value. Okay, and that's not to say that the value function is useless in practical RL. It's far from useless, actually. But no one uses it for the purpose of learning, like improving a policy. It has other uses, which we won't be able to get into in this course. But yeah. So control with state action values. And this chapter is like what it's like what everything's been leading up to. Okay, so it's like the finale, the grand finale is the most exciting time of the year. Okay, let's go. Control is the task of improving the policy, right? So, let's say this is like the state, the value. Let's say these represent policies, right? You want to go from the blue to the orange and I'm colorblind. I don't know what these colors are, but you want to go up, okay? Right? So model-free control. It is the goal of RL, a lot of RL, to improve a policy to get to the optimal one without knowing the dynamics, right? As I said, dynamics are hard to learn. So we want to learn the state action value function Q to do model-free control because as I said, it's impossible to improve the policy with V. But all of our algorithms that we've talked about have been for V, right? The Monte Carlo, the dynamic programming, the TD, it's all for V. So is there a method for Q? So I want you to start thinking about this, right? We've been talking about the state value function so far, but I want you to start thinking about going from state action pair to state action pair rather than from state to state, right? In our examples, we've been going from S to A, right? State S to state A. But now I want you to start thinking about going from state S, right action, to state A, up action, for example, right? So let's say, you have a mouse like getting to the cheese, right? If state to state would be for V, right? This. State action to state action, though, I don't know why it's cut off. That's weird. But state action to state action would be from, like this, right? It's from state 2, the right action, to state 3, the right action. Okay, start thinking about Q now, because Q is state and action. So can we do Monte Carlo for state action values? Yes, of course, right? It's exactly the same, taking the average, going to the end and taking the average. But this time you use the state action value instead. Okay. You count the number of state visitations, you average the returns. Right? Because recall the definition, right? Okay, hopefully we'll see this here, right? The Monte Carlo with the value function is this, right? If you guys remember. The definition of the Q is expected value of RT plus 1. So notice that this is still the return. It's still the return, but it's just now it's depending on an initial action and an initial state rather than just the initial state. So you can directly just sort of substitute this. So this is the Q function Monte Carlo update. You go to the end, right? You roll an agent out to the end of the episode. You get the return. You have a current estimate of the Q value for this particular state action pair. All right, and you do this update to update the value of that state action pair. Very simple, yeah. No, see, temporal difference uses the one-step TD. This is using the total return. Any number, yeah. For our example, if you recall, it was 0.5. Here it could be anything, yeah. Any number that makes sense. All right, this is the this is the Monte Carlo for Q. Everyone see this, right? It's exactly the same as V. You use the return to update. You still go to the end. Right? Nothing about a discussion of Monte Carlo has changed. It's just for a different number now. Instead of V, it's Q. But we won't talk about this because, as I said, Monte Carlo isn't really preferred in practice. So just know that this exists. And obviously, there's algorithms for this, but we'll move on to TD. Now, this is the TD update for V, right? Instead of using the return, it's using R plus gamma V ST plus 1, the next state value. And you can use Q for this as well. Okay, and now we get to the meat of this course. The next 3 algorithms I'll introduce are actually useful. You can actually use them in a real environment to solve RL problems. Everything before have been kind of, setting this up. Okay, you do policy iteration using V, but that takes really long, and no one, yeah, right? You have to know the model, right? Here is actually useful algorithms. This one's called SARSA. All right. The SARSA algorithm stands for state, action, reward, next state, and next action, the components that go into an update. So in order to do a SARSA update, you need the following components. You need the current state, you need the action you take, you get the reward from the current state, you need the next state you go to, and you need to sample an action at the next state as well. Okay. And the next action, A of t plus 1, is sampled from the current policy, whatever it is. It could be a uniform random policy. It could be a deterministic policy. It could be an epsilon greedy policy. I hope you guys remember what that is. This is the SARSA update equation. It's pretty simple. It's pretty similar to the TD for V, right? But this time, it's just, once again, the same idea. It's your current estimate for this particular state action pair. So in this case, this state action pair will be state 2 and the right action. So Q of this thing is the Q of this thing plus the step size plus the reward, or times the reward you get, which is 0, plus your estimate for the state and action at the next state. So at the next state, it will be state 3 and the right action, right? Once again, we're going from state action pair to state action pair now, not state to state. So this is going from 2 comma right to 3 comma right, okay? Minus Q of SAT. Very similar to the TD update, but for V, but just for Q. Oh, sorry. Bellman equations, right? Once again, remember how I said that the TD expression for V is a sample-based estimate for the Bellman equation for V? This is exactly the same thing. The SARSA update is the sample-based approximation of the Bellman equation for Q, right? In the Bellman equation for Q, there's two sources of randomness, right? The randomness of the environment after you take the current action, and the randomness of the policy at the next state, right? Where you select your next action. Here, we just sample, right? You take an action, right? The reward is sample from the environment, right? And you sample the next action at the next state, right? This represents the randomness of the next policy. So for this particular state and action pair, if you do this many more times, the assumption is that you'll see all the outcomes of the environment and the next policy. Does everyone understand why SARSA is the sample-based approximation of the Q value Bellman equation? Yeah. Yeah, this is TD. SARSA is TD, temporal difference learning, because temporal difference learning, unlike Monte Carlo, uses the estimate at the next time step, right? This is the value, Q value, of the next state action pair. Does everyone see this? So this is TD. It's one step TD, just like before, except instead of V, right? It's V. It's Q of S and A. Cool. Makes sense. Let's do an example. Let's assume that for this, particular situation, it's a uniform random policy, right? So you go left and right with equal chance. There's no randomness in the dynamics, all right? Deterministic. You go right, you'll always go right. Alpha is 1 and gamma is 1. Start with the state action pair, 2 comma right, right? Q is 1. Let's assume this is just your current value estimate, whatever it is. Q is 1. You get a reward of plus 0, let's say. And once you land in the next state, you sample an action from the uniform random policy. In this case, it just so happened to be the right action. It could have been the left action as well, right? But you just randomly choose an action at the next state. Why do you not choose an action at the current state? Because we're talking about the Q value. The action at the current state is already predefined for you, right? So there's no randomness there. There's randomness at the next state policy, so you randomly pick one. And let's say the Q value for that is 2. Okay, 3 comma right is 2, right? You plug it in. The new estimate for the Q value of 2 comma right is equal to the current estimate plus 0, which is the reward. Recall that alpha is 1, so normally this is just 1 here, plus the value estimate of the next state action pair, 3 comma right, and recall gamma is also 1. Normally there'd be a discount here, right? Minus Q of 2 right, which is 2. So this is the new estimate for the value. Does everyone understand the SARSA update? Yeah.
If we did
Um, no,
But, oh,
because you start in two, you make a move, but you're not like um I don't think you're not like actually sort of you're not actually like going to like
like you actually move like this.
yeah, it's more of like a it's more of like a thing used for the value update. It's not actually you're moving right. Because if you go right, you land in three, there's a chance you could immediately go left, right? This three comma right is just used for the value update. It's just used for this. Do you see that?
What happened on the next? Like,
Yeah, so you'd start um you'd start three and you would take you would sample like an action, right? But once again it's not random here because this is like okay. So this is policy evaluation, right? You know all you have like you have a table of all the Q values, right? In this environment, there's only like 8 Q values, right? Because for state one, you have left and right. For state two, you have left and right. There's 8 total numbers you have to update. What you do is you can just sort of go through them all in a for loop. You just loop through them all, right? And you use that to as the update. Do you get what I'm saying? Like it's not like your it's not like in this case, I don't want you to think of it as like moving through environment. Just think of it as like you start in this state, right? You pick a particular state action pair in this state, right? Let's say the right action. Okay. All right. You sort of simulate it, you take it, right? You see where you end up, right? And in that state you end up, you sample an action from your current policy and you calculate this number and you move on to the next state value. It's not like you then go to that state. I mean, you could, I guess, but I you could do that, but I think in practice, I would for SARSA and Q learning and this, you can just sort of go through the states. You can go through an episode. Yeah. So actually, you know what? Sorry if I'm confusing you. So yeah, I think you can start at two, you go right, you go to three, and then you can yeah, you can do three. The next time you start with three and right. Yeah, I think you can. Yeah, sorry. I was thinking of so I mean another way of implementing this, which is not like this, but yeah, you can just do what we did with the value. You go to the end and you update as you go. So yeah, you can do it here as well.
you could just also start at a random state each time.
I think you can, yeah, because this is like, you know the policy, you can just, yeah, you can, but you can also just go through what like one by one. Yeah.
Make the biggest possible.
No, you're trying to find the actual Q, right? Because remember, the Q function depends on the policy, right? For this particular policy in this environment, right? The policy being the uniform random policy, there's a certain Q value. You're doing policy evaluation. You want to find the actual Q. So it would make sense that if you look at this environment, the Q value of this action, 4 right, would be much higher than the Q value of 1 right because it's closer to the cheese, right? It's closer to the actual goal. It's not like you want to make everything as big as possible. You want to find the real Q value. So does everyone understand SARSA? Yeah. Yeah, I think you can. I think you can. That's what Monte Carlo does, I think. You can just choose any state action pair, just go. Yeah. This is just SARSA, like algorithmically depicted, right? Initialize Q of A. You start with some random Q value estimates, right? Um, you initialize S, so you start from some starting state and then you go from there. Yeah. No. Q learning is a separate algorithm, which we'll get to.
Also, SARSA.
It's called SARSA is learning the Q function, but it's not the algorithm called Q learning. Yeah. So this is just exactly what you do, right? You sort of take action A, observe R. So this is what he was talking about. You go through the episode, actually, right? You start at some state, you take action A, observe R, and you go to S prime, and then you choose A prime from S prime, so the next state action pair, using the policy, right? And then you do this update, you then you restart from the next. So actually, so to answer your question, yes. So in this case, at the next iteration, you would start from 3 comma right. Right. And then for the next iteration, you go 4 comma right, if that's where you picked, and you reach the end, and then you reset at 1, and then you repeat. But this time, since the policy is random, maybe you'll choose 2 comma left instead for one of the iterations. So I hope source is clear. Yeah. Yeah.
Yeah, like
Yeah.
if that value to update the first the starting state action.
No, this is only for 2 comma right and 3 comma right. This is not for this is only for 2 comma right and 3 this is only for 2 state action pairs. This number Q equals 1 is your current estimate for the state value of 2 comma right, and Q equals 2 is your current estimate for the state action pair of 3 comma right. Yeah, so then you update the value for Q like so. Yeah.
So that's find a Q value will be a policy.
Yes, precisely. So this is what you would do in policy iteration. Once you find your Q value, you would just do argmax QSA. You just pick the largest in each, and that's your new improved policy. Yeah.
So we like fully learn the Q value.
Yeah, you'd have to know the Q value for every state action pair. That's policy evaluation, right? You're learning the Q value for all the state action pair, and then you would just greedily pick the best action, and then you repeat, and then
We really think that
no, that's called policy improvement. Policy iteration is policy evaluation plus policy improvement. Okay, that's SARSA. It's just TD, but with Q values. Right? Okay. Now there's something called expected SARSA. This is a separate algorithm. What is expected SARSA? Let's take a closer look at SARSA, right? Recall that this action is sampled from the policy at the next time step, right? Meaning that we pick one action according to the policy. But why do we need to do that, right? Because we already know the policy. Right? That's something the agent knows. Recall the first week. It's inside the agent. You know the policy. So why do we need to sample, right? Because recall that sampling increases variance, and we don't like variance. We want things to be stable. So if you look at the Bellman equation for the Q function, right? You have this thing here. You can directly compute this thing because you know the policy. You know the policy at the next state. You can't compute this thing because you don't know the environment, but you know the policy. So what we can do is we can just take the expectation directly. So that's expected SARSA. The difference between SARSA and expected SARSA is basically the same, but instead, the Q value of the next state, you take an expectation over the policy. You average it. What does that mean? Okay, let's say these numbers are the Q values. So there'll be 4 actions here, right? 4 actions at this particular state. This quantity here is computed by weighting these values by how likely they are under the policy. Right? Does that make sense? 0.1 times 0, 0.1 times -1, 0.7 times 2, etc. Right? So it's 1.4. So that's this quantity here. Once again, we're not with SARSA, what we would have done is randomly picked one of these Q values according to the probabilities listed in this policy. If there was SARSA, we probably would have picked a Q value of 2 because it is the most likely Q value under this policy. But for expected SARSA, we instead took the average. I hope that's clear to everyone. Yeah. Yes, exactly. Yeah. If this were SARSA, there would be 4 possible updates, right? 1 plus gamma times 2, right? Corresponding to this. 1, let's assume that's the reward you get, okay? Let's assume that's the reward you get. 1 plus gamma times 2, 1 plus gamma times -1, 1 plus gamma times 1, and 1 plus gamma times 0, right? And these possible updates would be sort of how likely they are depends on the policy, right? So there's a 70% chance you'll do this update, 10% chance you'll do this update, right? But for expected SARSA, and so if you like average out these updates, you'll get that this is around 1.0 plus gamma times 1.4, right? But notice for expected SARSA, you like directly calculated this expectation, right? Recall, let me go back up, right? You already weighted each Q value by the policy. So instead of randomly sampling many times to get an expected update of 1.4, you can directly calculate this update. Does this make sense to everyone? Why the difference between SARSA and expected SARSA? Okay. Now, the expected SARSA update example is this, okay? Once again, let's assume it's this, right? You start with 2 comma right, this state action pair. Let's assume the estimate for the Q value is 1. Let's assume you get a reward of 0. Let's assume that the next state action pairs are, you don't need to assume actually, you know that the state action pairs at the next state are 3 comma right and 3 comma left, right? Corresponding to Q value of 2 and 1, right? Let's assume that these are the estimate for this. Recall for SARSA, we only cared about 3 comma right because that's what we sampled from the policy. But here we care about all the possible actions here. So you just do the update, right? Q of 2 comma right is equals to Q of 2 comma right plus 0. But this time you weight both of these Q values by how likely they are under the policy. That's the expected value, right? So since it's a uniform random policy, you're equally likely to go left and right. So that's why you weight them like this. And by doing the calculation, you get 1.5. So this is the different way of updating the Q value using expected SARS. Does everyone understand what's the difference between expected SARS and Q learning? The bottom line is, because you already know the policy, you don't need to sample from it. And therefore, by removing this sampling, this random sampling, you are decreasing the variance of expected SARSA compared with SARSA. Does everyone see that? This means that the algorithm training will be more stable and more effective. That's why expected SARSA might sometimes be preferred over SARSA. But why would SARSA... Okay, give me a situation where SARSA can't work. Expected SARSA can't work, right? Let's say you have yeah, go ahead.
But
Yes, precisely. If you have infinite amount of S actions, this expectation is not easy to take because you have to do the integral over all the actions. And that is extremely expensive computation or impossible to do for actual action spaces. So in that case, you have to use SARSA. You have to randomly sample from the next policy. It is precisely for this reason that you don't really see expected SARSA in actual high-dimensional like action space algorithms. I'm just presenting here as another option for you. Okay. Okay, now this is like the main character of the TV show, if you will, like this guy here. You know, he's the main character of RL, I say, Q learning. I have a double box just in case I was being too subtle. Yeah. This is the algorithm which you should know, which is the basis for almost all other RL algorithms. It's basis for everything in RL almost. Let's take a closer look at SARSA, okay? Recall that the Q function depends on the current policy. Therefore, the action A of t plus 1 is selected based on the policy you are currently following. If you're following a uniform random policy, then the AT plus 1 will be selected randomly, right? Therefore, the Q function being learned by SARSA is the Q function for the current policy. That is why I said you could use SARSA for policy evaluation, right? You learn the Q function of current policy. Same with expected SARSA. You also learn the Q function for the current policy because this expectation is being taken with respect to the current policy you're following, right? If there's a different policy, you'd be learning a different Q function, right? So both of these algorithms, expected SARSA and SARSA, learn the Q function for the current policy, not another thing that we might be able to learn, right? So in order to get the optimal policy, you have to learn the Q function, do policy improvements, and et cetera, et cetera, et cetera. But yeah, so this is good, right? We can do model-free control, right? We can improve the policy with a model using using SARSA and expected SARSA. But can we learn anything else, right? Recall that, what if we could skip all that and directly learn the optimal Q function, right? If we could directly learn the optimal Q function, we don't need to do all this policy iteration stuff. We can directly get the optimal policy by selecting the best Q according to the optimal Q function, right? Does everyone understand why SARSA and expected SARSA are not learning the optimal Q function, right? Because it's following the current policy. The next states are sampled from the current policy. What Q learning does is it directly learns the optimal Q function, model-free. Recall the Bellman optimality equation from last week. This is for the optimal Q function, right? Recall that instead of taking the expectation of the actions, like the Bellman equation for the Q function, the Bellman optimality equation, because you only care about the best possible outcome, you take the max over the next state action pairs. So just like how expected SARSA and SARSA are sample-based approximations for the Bellman optimality for the Bellman equation, Q learning is the sample-based approximation for the Bellman optimality equation. So therefore, this allows Q learning to directly learn the optimal Q value. And once you get the optimal Q values, it's basically like you just learned the optimal policy. This is why when I said value-based methods in reinforcement learning, ones that don't have a policy, right? If you recall, the classification of RL agents. Some agents don't even learn a policy. All they need to do is learn the optimal Q value, and they already have the policy because they can simply get the policy by doing the argmax or some variant of it. Okay, this is the Q learning update rule. It's very important, and this form of update rule appears in a lot of algorithms down the line. It's the current value, so I'll get to a question later, plus alpha, R plus, recall for SARSA, here you would sample an action. For expected SARSA, you take the expectation. For Q learning, you take the maximum Q value. Okay? You don't care about the current policy anymore. It could be anything. It could be a random policy. It could be anything. You always deterministically pick the highest Q value, and you subtract the current estimate. So here it is exactly that, right? Let's say you have SA and R. Now you're at S prime the next day, and there are three possible actions. For SARSA, you'd randomly pick one according to a policy. For expected SARSA, you'd average them. For Q learning, you look at these actions, you pick the best one. Let's say if this action is the best one, you pick this one for the update. Even if it has a probability of 0.01 in the current policy, you pick this one for the update. Yeah. Uh-huh. No, not always. Sometimes in certain environments, the reward is a distribution. You take this action, you might get 5 reward or 7 reward or something. In every example we've done in this course, the reward has not been a distribution. It's been deterministic. I've said that if you take this action, you'll definitely get this reward. But in sometimes, let's say it's a slot machine, you pull it, you might get a reward of 10, you might get a reward of negative a million, right? You just lose all your money, right? The reward might not be deterministic. Yeah, exactly. It's a small difference, but it makes all the difference. This is a comparison between Q learning and SARSA, right? Q learning does the max. It approximates it's a sample-based approximation to the Bellman optimality equation, whereas SARSA samples from the current policy. It's an approximation to the Bellman equation for Q. So just sort of putting it into words, right? At the next state, Q learning does not use the current policy to sample the next action. Okay, remember this is very important. Let's say the best action at the next policy, well, the best action at the next state under the currency has a probability of 0.0001%. You still pick it in Q learning. In SARSA, you won't pick it, or you might, but it's got a very small chance of doing so. Okay, so therefore, because Q learning is not learning the Q function for the current policy, because it's not picking actions according to the current policy, it's picking actions according to a greedy policy somewhere, right? It learns the optimal Q function. SARSA, because it's picking action according to the current policy, it learns the current policy's Q function, but Q learning does not. This distinction is very important. Do you guys understand that? Please ask me if you have any questions. Yeah.
So the policy is the facts.
Kind of, yeah, exactly. Yeah. Technically, that's the policy for Q learning. This is just the intuition behind Q learning, right? It's basically saying that, like, even though I'm behaving randomly now, meaning that even if I have a random policy right now, in the future, I will always make the best possible choices. I assume, that's why I'm taking the max. I assume in the future, I will always make the best choices for this environment. I'll use this assumption, the fact that I'll always make the best choice, to improve my value estimates right now. That's sort of the intuition behind Q learning. Okay, sort of, yeah, express it another way. So let's try an update, right? So let's assume, once again, the starting state action pair is to and right. With a Q value of 1, you get a reward of 0. There are the state action pairs at the next state. Okay, what would you do for Q learning here? Which value would you use to update the value of 2, right? Which one? Right, this one, right? Q equals 2. Even though it's a uniform random policy, you don't care about that anymore. You just pick that one. So here it would be the same. Q of 2, right plus 0 plus Q of 3, right minus Q of 2, right equals this, equals 2. Right, yeah.
Why is Q there?
I just assume it's 2. All these values are random. I just assume. Yeah, you can assume that, yeah. So assume the value here is 2. Okay, I'm not saying this is the real value, but it probably is because, like, if you think about it, I mean, it's close to the final state, so it makes sense that the right action would be better than the left action, right? So yeah. Although now that I think about it, if the reward is 0 per time step, it doesn't really matter. So actually, this is not that accurate, but it is what it is. Just assume this is like, yeah, the value. So Q learning is sort of algorithmic-fied. It's basically what I just talked about before, right? But you use the max to do the update. Okay, this is the, yeah, go ahead. Yeah, yes. It's once again in tabular, like finite action spaces, it's guaranteed to converge to the optimal value function, optimal Q function. Go ahead. Yeah, so at this, you look for the biggest Q at the next state, right? For expected SARSA, we average this based on the policy. For SARSA, we randomly picked a action according to the policy, but here you don't care about the policy at all. You always like blindly, deterministically pick the largest Q value at the next state. And this will enable you to learn the optimal value function, Q value function. Yeah, I hope this makes sense, everyone. Q learning, very important. Yeah. This is the final part of the lecture, the course. Should you always use Q learning? Q learning seems to be much better than SARSA and expected SARSA, right? Because it directly learns the optimal Q function, right? But let's consider the following environment. Okay, this is a very famous environment. It's called Cliff World. You have this grid here. There's a cliff here where if you land in a cliff, you get a reward of -100. Otherwise, you get a reward of -1 per time step. So the idea is you want to escape this maze as quickly as possible, or not a maze, but go from S to G as fast as possible without falling into the cliff, right? The actions are left down, left and up, down, left and right, right? If you fall off the cliff, you immediately go back to the start, right? You're dead basically. You go back to the start. But the transitions are deterministic, no randomness. Okay. There's some number as a discount factor, okay, whatever, less than 1, greater than 0. Okay. And let's assume we start with an epsilon greedy policy. Do you guys remember what that is? Oh, here's a recap for you anyway. It's a stochastic policy where most of the time you pick the best action. But with a very small probability, you take a random suboptimal action. So this enables exploration of the environment, right? If you always go with the best action, you're sort of greedily like narrow-sightedly charging towards the goal, like always picking the best option. But if you explore, right, if you have a small chance of exploring, you can maybe see other parts of the state space that you normally wouldn't see. Q-learning in Cliff World, okay? Because the next action is always greedy, okay? When doing this Q update, the epsilon greedy policy is always ignored when doing the update. The agent only explores when it takes an action, but not during the Q value update. Does that make sense to everyone, right? Because you're taking a max here. It doesn't matter if epsilon is like really high value. You always greedily take the next action. So Q-learning will learn the optimal policy and the optimal Q function for this environment. Can someone tell me what that would look like for this environment? Like remember, you want to avoid the cliff, right? And you want to escape as fast as possible. So what would that look like? Right, exactly. This is what Q-learning will learn. Pretty good, right? Yeah, it's pretty solid. But what will SARSA learn? Okay. Recall that in the Q value update, the next action is sampled from the current policy, which is epsilon greedy. So the Q function that is learned is the Q function for the epsilon greedy policy, not the optimal policy. Do you guys get that? An epsilon greedy policy cannot be optimal here. Because if it's the best policy, why do you need to randomly explore somewhere? If it's the best policy, you know where you want to go, right? So epsilon greedy is a suboptimal policy for this environment. Does everyone get why that is? So if you do this, okay, SARSA will learn this. But what I want you to, which path do you prefer? Like, let's say you're like actually like a robot or like a pedestrian. Which path would you prefer? Keep in mind, there's a giant cliff there. Right. You would prefer the one by SARSA, but notice that it's actually a worse policy than the one learned by Q-learning because it takes longer to get to the goal. Yeah.
It's such a guarantee, that exact fact.
I think yeah, I think so, yeah. Maybe. I don't know. This is from like this example is from a textbook. They did the SARSA and stuff. So and this is what it got. So yeah, maybe. I think it is. So that's interesting, right? Like I just want to get across this idea that in reinforcement learning, right? Why this makes this field so complex. Sometimes, you know, the best isn't always the best, right? Even though Q learning escapes really quickly, it's a very unsafe path. But for SARSA, it might be suboptimal, but actually you might want to prefer that if you're like a robot. You don't want to lose your robot on like Mars or something to a cliff. So let's think about this, why this happens a little bit, right? Let's assume the agent is at the edge of this cliff. The greedy action is to move right? Because you're getting closer to the goal. However, due to the epsilon greedy policy, sometimes the agent will make a random move, like going down, falling off the cliff and getting negative 100 reward. So SARSA, though, will update its Q value using this bad experience, right? Meaning that the Q value near the cliff will be very low. So this could be an update. So let's say you want to find a Q value for S comma right in this state, right? The right action in this state. It'll be the current estimate plus alpha minus 1. That's the reward you get, right? That's the reward you get for transitioning in this state. Recall, reward is negative 1 per time step. Plus gamma times negative 100, right? Where did the negative 100 come from? It's because due to the epsilon greedy policy, the agent might have accidentally picked the down action, getting a negative 100 Q value. Okay, minus Q of S right. So therefore, the value of S comma right will be low, will be like kind of low, right? Because for the other cases where it picks the up action or the left action, you won't get negative 100 here. You get like negative 1 or something. So it won't be like crazy low, but it will be low. Sometimes it will get this update. Does everyone see why SARSA does this? Now this negative 100, you know, it might, yeah, it might not be like the most accurate value here, but just the intuition is there, right? Sometimes it'll fall off the cliff for SARSA. However, Q learning will never even consider the down action, right? If it's at this state and it goes right, it won't even consider the down action. It will look at the action that goes down and see it achieves a terrible like value and just completely ignore it. Okay. Even if it falls off the cliff, it will just ignore that. So Q learning will not use the bad experiences of falling down a cliff in its Q value update. So what it will do is in this state, it will look at S comma right? It will get the reward and it will take the max over A prime so up, down, left, and right. It will take the maximum value there. And this maximum value 100% is not the down action. It will basically ignore the down action all the time. That is why Q function or Q learning has absolutely no notion that there's a cliff right there. Well, it does, but it won't care. It will ignore that experience. Right? It won't even consider the down action in its max because you know it's bad. That is why Q learning is great. It's extremely important. It's probably the best algorithm, but sometimes you have to be nuanced in this regard. Okay, so quick recap. We're kind of out of time here. Dynamic programming, Monte Carlo update, TD learning update. All right, different sort of levels of updates. This is the one for Monte Carlo, V for Monte Carlo. This is the equation for TD, one-step TD. This is how you pick the best policy according to the Q function and why you want to learn a Q function. And this is the Monte Carlo update with the Q function, right? Just replace it, right? You still use the return. Right? This is SARSA. This is expected SARSA. Okay. This is Q learning, where you take the max and it learns the optimal value. And yeah, that's the end of the main lectures for this course, actually. What's next? So there's another session next week. I recommend you come, but that session is advanced RL topics. Like you might not understand much in that, but just to talk about research and like what actually is used, where RL is actually used for. In this course, the algorithm that I would argue is the most important is Q learning because that is actually used. But yeah, it's still important to understand everything else. And AI Squared, this is the tournament that happens in your fall reading week where you can learn to apply RL. So yeah, please keep in mind that. Yeah, yeah. So just quick, summary. For future directions for reinforcement learning. To solve a reinforcement learning problem, you can find two things, right? The optimal policy or the optimal Q function. Okay. We have spoken about methods to find the optimal Q function in this course, right? Monte Carlo with the Q function, SARSA, Q learning, expected SARSA. And they are called Q function methods because they find the optimal Q function. We did not speak at all about methods which don't find an optimal Q function and sort of only find the optimal policy. Okay. These methods are called policy gradient methods. And we didn't cover them at all because they're beyond the scope of this course because you need to understand gradient stuff. Gradient stuff. I would argue that Q function learning and policy gradient methods are like families of algorithms, okay? And in each family, there are important RL methods that are widely used today. Here's my own grouping of these methods. These are all advanced RL, more advanced RL algorithms, but they're the ones that people actually use. Like if you wanted to solve an RL problem, like the first thing a researcher will do, okay, let's try soft actor critic, for example. So I'm not going to explain them now, but I just want to drop these names in your head. So maybe if you're curious, you can look at them later. Okay. PPO, proximal policy optimization, is the one used to train ChatGPT. It's the one that's tunes ChatGPT. Okay. Soft actor critic and twin delayed deep deterministic policy gradient is the extension of Q learning to the continuous action space and state space. Okay. So these are the two tracks, I guess, you can go down. I would once again, you don't know what these things are, that's fine. I would strongly recommend you sort of, if you get time, you're curious, you can look at these algorithms. I would start with Q learning, deep Q networks, all right? Because you have some background in Q learning. The policy gradient stuff, initially the math is a little bit complex. So yeah, future directions for you to explore. I could talk a little bit about these algorithms if you're curious afterwards, but yeah, that's it for this course. No, not yet. There's one next week, but that's the end of like the content for this course. Next week we'll just be showcasing research and everything. What I do and one of what like the other person's coming to talk about is something called offline reinforcement learning, where So this whole course, I've been saying that reinforcement learning requires interacting with the environment to get experience. But offline reinforcement learning is where you can't do that. It's just a static data set, right? And so if you're curious about how that works, feel free to come and talk to us next week. But otherwise, yeah, thanks you guys for coming, even though it's so busy. I will stay for another like 10 minutes. And if you have any questions, if not, yeah, please fill out the feedback survey. Let me know how I've done throughout the course. Thank you.